So the title of presentation is Calibration of Vehicle Following Models Using Trajectory Data. The trajectory word here, let me make it very clear. Trajectory is a micro simulation based or micro level interaction when there are a group of, let us say you might be traveling daily and you are driving. So always there will be 3-4 vehicles in surrounding of your vehicle. So your presence is going to affect definitely the other vehicles also. So it is not a lane discipline, as you know already. So what I mean to say is, I'm not going to explain the whole heterogeneous traffic condition here, but what I want to say is, there will be always effect in that particular group. So there is no perfect car following theory, or there is no perfect leader and following behavior, or a particular pair-to-pair, okay, kind of behavior that one car is following and other car also following. It may not be really the case for that particular matter, okay. This may be there on some of the freeways or intercity expressways in India, like Pune-Mumbai Expressway, or it may be on Delhi-Gurgaon Expressway, slightly. But there are also some vehicle categories like two-wheeler or auto rickshaws. They actually induce in and then they will destroy this car following or vehicle following behavior. Okay. So on this backdrop, I am going to talk to you, and you can just have a look and then give your feedback to us. And if any suggestions are also there, you are welcome. The outline of the talk is as follows. It is, I'll be giving you some introduction and challenges. Then there are some past studies by us also and by many other researchers in Indian conditions from IITs and other NITs. We have framed certain objectives, methodology. There is some theoretical base for Weidmann 74 and 99 models. Okay, I hope that everybody knows that these are the inbuilt Weidmann, okay, the person who has invented this car following theory based on psychophysical models, and it is induced into VISIM at present 74 and 99. Of course, 99 is a much upgraded version to 74 because of more parameters for calibration. So we tried our level best actually to calibrate for both of these models, and then trying to show you how accuracy can be increased with this particular approach. Study area, of course, we have selected 2 study areas. One road is in Chennai and another road is in Delhi, Delhi-Gurgaon Expressway. Everybody must be knowing, most of you are from Delhi. And then, of course, they are also from Gujarat. So, anyway, you must be having some idea about Delhi-Gurgaon Expressway. Then calibration. Then we have also created bottleneck in VISIM and then tried to see what is its impact on trajectory data. So, trajectory data is also collected from field, and also trajectory data is plotted through simulation model. And then we can do many things once we have this particular tool in hand. So that is what okay I'll be actually discussing. There are enough challenges. I told you that of course word simulation looks very good and it is very handy tool, and then okay, but then definitely if there is garbage in, garbage out will be there. So we have to be uttermost careful. As you know that we have to calibrate these parameters well, then only you can apply it in field. So for that purpose, always challenge is there that how to induce or how to basically include this following theory or following behavior. Okay, following theory is what? How basically there is an effect when you are driving a car. Somebody is on besides you laterally as well as longitudinally is going to affect your performance, or also your performance or your driving behavior is also going to affect somebody's other behavior. That is to and fro, or that is one to one, or it may be even to be very precise, there is not only one single vehicle as a leader. There can be 3 vehicles which are in front of you, and there will be little the effect of all those vehicles on your behavior. So that is why it is really little difficult, and there is a lot of challenge basically in replicating this particular condition under using this VISIM under Indian condition. And that is the reason we have tried to develop some approach. That is what I will be talking about. There are certain studies which are developed, okay, which have been carried out all over the world. Professor Ranjit Kar is in Auckland University of New Zealand. Then Sandeep Mneni, okay, and then Peter Vertisk. They have developed certain calibration procedure. Of course, Professor, I think Vertisk is from PTV only. He was with PTV. And then there are some other efforts from China. There are efforts from Professor Tom Matthew. From IIT Bombay, and then we have also done some studies on this particular aspect. There is Peter Vertis also one more he has done, and then so many items are there. But when it comes to Indian conditions, we don't have exact methodology that how these parameters are arrived at. Okay, methodology is there that is developed based on soft computing techniques, particularly which was developed first by Professor Tom Matthew from IIT Bombay, where the parameters are taken from PTV user manual, and then based on the type of parameter, there were some ranges given, minimum and maximum value, and then GA was applied, and then GA is basically genetic algorithm. Okay. Thereafter, through optimization, the value was fixed, and it was a more of a soft computing approach. But the challenge was there was no availability of actual field-based observed trajectory data, through which we can actually study the behavior of that particular following behavior. So with that objective and motivation and challenge, we started this particular study, and that is what I am going to explain. So the challenge is what? Identification of true leading following pairs in heterogeneous traffic environment. This is extremely difficult task, is a challenge still. Many people are working on this particular aspect at present in IIT Madras, IIT Bombay, SVNIT Surat, and all other NIT also maybe. So I hope that we should come up with certain good methodology for this. Of course, we have calibrated Wideband 74, then we have calibrated Wideband 99, different parameters. Here there are 3 parameters, here there are some 9 parameters are there, out of which we have calibrated 7, and 2 we have assumed as default. Then we have done microscopic validation. Of course, microscopic validation is very, very difficult. As you understand, under Indian condition, it will be extremely difficult to validate based on microscopic observations. So at present, we are restricting our study to microscopic validation. Once we have done all these things, then we have actually simulated the bottleneck and then try to see the effect and utilization of infrastructure and its effectiveness. This is the methodology which generally we have, just now I have discussed about it. These are the locations. One location is Delhi-Gurgaon Expressway and another is in Chennai. The motivation behind this was, of course, you can ask us question that you are in Surat, how come you are having this particular data? So naturally, because we were earlier, my place of work was near to Delhi, so I have a lot of traffic data, video data. From that, I got some trajectory. And then Chennai also, we got some friends through whom we got some video data, and then we have tried to use that particular trajectory data. And also, it is available open source. So that details also we can share with you, that this trajectory data is also available open source. Anybody can access it, anybody can use it. First of all, let us say that before we do any more discussion, I think it is very important that whatever data we have, that we should share all over India. Because if you don't share that data, then it is really a defeat of research actually. That is what is not happening. So that first of all we should start sharing database. So after this presentation, if those who want data, they can take data from us. These are the study sections. You can look at it. This is Delhi-Gurgaon Expressway. And the video data was collected. This is 65 meter. Okay. Basically, we tried to focus on 3 electric poles, and then we have tried to develop the trajectories based on this particular video data. This is Delhi-Gurgaon Expressway, and this is Chennai study section. You can see the location of the camera is at a vantage point from where we can easily get something like 200 meters or 250 meters. So for this kind of study, it is extremely important that we should have a very good vantage point, because without which we cannot get anything. We don't have any kind of automation, we don't have any kind of instrumentation on our roads. And even if it is there, it is not going to work well for our conditions, as you know, right? So it is most important step that we should have this particular vantage point from where we can get this, and then we can develop trajectory data. These are the details. These 2 study sections, these 2 roads, one is urban arterial road. Of course, it is multi-lane road because it is 6-lane divided. And then the other one is Delhi-Gurgaon. It is 8-lane divided, as you know, with paved shoulder. And it is not exactly urban arterial, but it is a kind of multi-lane high-speed corridor. But it is still urban because it has that character. It is expressway by name only. It is not really expressway. Okay, I hope everybody agrees with me. Even sir is there from rights. So I must acknowledge his presence. Delhi-Gurgaon Expressway definitely is a multi-lane urban road. It is not exactly an expressway because there is a partial entry-exit points, and the behavior is not exactly like expressway. Okay, so this is how this is the motivation which we carried, and then we took these 2 roads for our study. We have developed trajectory data for 15 minutes, and of course more data is available. We have used 15 minutes data only, and then Delhi Gurgaon section also we have 20 minutes trajectory data. So that means what? Every 0.5 second how a particular vehicle is moving ahead, that we have tried to catch on time space plot. And through this, if we have couple of trajectories together, then we can have a very good behavior out of it to study. This is the composition of traffic. To be very precise, Chennai section is having a lot of two-wheelers, and Delhi section a lot of cars. So this is how it is different. Then this is the trajectory data which I wanted to tell you. This is how it was developed. So there are, you can see that on x-axis there is a time, seconds, and then on y-axis distance. This is time space plot. Okay. Very easily one can note it down that Chennai trajectories, they are almost parallel to each other. That means the flow condition is not very, very high, and it is not at the same time very, very low. So it is a kind of moderate traffic flow condition under which there is some kind of following behavior which is taking place, and that is why that particular study section, or that was the study Chennai, that particular traffic flow data was selected for this particular study. Because unless and until there is any kind of following behavior, there is no point in taking that particular data. So this is the trajectory data which I was talking to you. Those who are interested, please have this trajectory data and try to work on this particular model. Okay, I am just presenting here one of the possible ways. There can be n number of possible ways through which you can come up. This is a denser spectrum, and this is very micro level spectrum. You can see that. Of course, you can see there are many trajectories which are also laterally combining. And that means what? Laterally overlapping. That is nothing but lateral kind of behavior is present there. So if we give this kind of trajectory data, nobody is going to get any kind of thing. So that's why what we thought, that let us segregate it based on lane first of all, and then try to induce only those trajectories where there is a overlapping between the half of the vehicle is in one lane and half of the vehicle in another lane, and then those let it be overlapped over that, and then from that we get certain idea that how a lateral behavior can affect the performance of present vehicle. So this is again a denser spectrum, and this is this is a micro level spectrum, and this is a huge spectrum. So you can see that this is how it looks like. You can see that these trajectories are quite closer. That means this particular volume is very, very high. It is almost near to capacity, around 6,700 vehicles per hour, and the earlier one was around 1,500 to 3,000 vehicles per hour. So that was 0.5 V by C ratio, and this is almost near to 0.9 V by C ratio. Yeah. So this is the challenge, that how to identify exact leading and following behavior or leading pair, because there are 4 or 5 vehicles together. So what makes it that which vehicle is leader and which vehicle is literally a follower? So for that purpose, as I told you, that we have categorized into lane wise, and then over that those which were just on the lateral part, okay, partly on one lane and partly on another lane, those trajectories were overlapped over these trajectories, and we tried to find that there are a lot of possibilities that may be two-wheeler, that may be car, that may be anything, okay, any vehicle category that can be. So because of presence and size of that vehicle also, of course, it is going to vary the behavior. So this was dealt in. Then we thought that, okay, one way how to analyze this behavior. So we have to definitely create a plot which explains on x-axis what is the relative speed between two vehicles, and on y-axis what is the relative distance. This is relative speed and this is relative distance. That means if somebody is there ahead of me, between us, what is the relative distance and what is the relative speed. So that is these are the two parameters they are very well proven that these are the two parameters which are actually quite handy in knowing the behavior of drivers. And of course, based on vehicle type, we can easily identify that. So you can see that typically in Indian condition, we can find this kind of thing: vehicle 1, vehicle 2, vehicle 3. Vehicle 2 present here, that doesn't mean that it is always going to affect the performance of vehicle 3. Okay, this is the thing which we have learned from our experience. What we found that vehicle 2 might be just going. It is just, since it is a multi-lane road, it might be just passing this particular vehicle 1. So it is not having any effect basically. So for that purpose, we wanted to identify exact following pair, or there is some kind of following effect. So for that purpose, we tried. This is, for example, the orange one is vehicle 1 and vehicle 3. Then this is the vehicle 1 and vehicle 3, and this is vehicle 1 and vehicle 2. So you can see that vehicle 1 and vehicle 2 is just passing vehicle 1. It is not having any kind of impact. And that is why this is a kind of hysteresis actually. What is this? What do you mean by this? It is coming this right side, left side, and again it is going back, and then there is some kind of hysteresis. That means what? This is the behavior that you are or a following vehicle is actually is accelerating, decelerating, accelerating, and because of that there are changes in relative speed and relative distance. And this is what we try to catch in this particular study. So in our opinion, if this is the case, then this is perfectly following pair, because it is exactly this is the origin. That means this is the let us what is this negative point? I am standing here, I am a vehicle and somebody is following me. So on my right side is going to be positive, on my left side is going to be negative. Okay, so that is what is the significance of negative and positive. Based on that, we found that those which are near to your current position, that means what perfect following behavior is what? You are following exactly on axis. It is not like lateral behavior on either side. So those which are exactly on that particular axis, they are exactly following pairs naturally, because they are going to be all the time following each other perfect. There is no staggered behavior actually, there is a perfect following behavior. Similarly, we have identified staggered behaviors also, those which are very, I will show you some other examples. You can see here for similar kind of combination, another example was like this. So here you can see that almost all three are in. For this case, you can see that all three are having same kind of behavior. Okay, only thing is what is changing. This must be vehicle, this must be immediate to this leader, and then this must be far. That is why the difference is, high. You are more and more closer, then you are going to have the relative spacing will be less, and then also relative velocity also should be less. So this kind of behavior we try to study, whereas in this case you can see that the relative distance is very high. That means but still you can find this particular thing, relative speed here and here it is almost same, even though relative distance is lesser or more. So that means here this particular vehicle is following in a better way as compared to this vehicle. But overall there is effect of all three vehicles which are present in that particular combination. So what we try to do, we try to see number of trajectories like this, and then you can see that, for example, this particular vehicle is not having any impact. There is certain other distraction which is taking care, okay, which is affecting actually performance of this vehicle. This vehicle, there is something happening here, then again it is coming back here, and like that. So with this methodology, what we try to do is, when there is evidence of perfect following behavior, and then little bit hysteresis within some kind of threshold value or acceptable to us as a researcher, we have chosen all those trajectories and then pull together all those things. This is one more very good example of pairwise hysteresis. This is just one pair. You can see that initially difference is very high, and then as you close up, you can find that their relative speed and relative distance is coming down. That means this is a perfect following behavior. So I am interested, maybe one of the parameter is somewhere here ABX and somewhere it is AX. So if I try to get it based on vehicle type, probably I am trying to develop some kind of vehicle-based simulation, vehicle-based following behavior in my particular system. Okay, so likewise we have done it. So all the identified pairs for these particular cases, we have included only those which are perfectly following, and then with a lateral gap of almost 1 meter, all those pairs with relative speed and relative distance are pulled together, and we have put into a form. You can see that some of the trajectories relative distance is 100 meters, and some of them they are having just less than 1 meter. That means we have almost all kind of behaviors, which are actually hidden into this particular hysteresis. Just try to imagine the driving behavior cup which is proposed by Weidman, which is available in PTV user manual. You can see that almost is a kind of replication under Indian conditions. But then only thing is, we have to go for this kind of cups, driving behavior cups for different vehicle types. So let us say this is two-wheeler hysteresis. You can also find different types. This is two-wheeler hysteresis, this is car, this is bus. Bus you can find it is quite, there is no much deviation. It is quite close to the x-axis. Whereas in case of two-wheeler and car, you can find that there are a lot of distractions. The blue one is Delhi, Chennai is the orange one. You can see here. So you can see that even for a smaller spacing, there is very high speed difference. There is no less speed difference. So by virtue of this, we can even try to know the behavior of different cities. This is just Chennai and Delhi. You can try to overlap many other histories on this and try to see that up to what level a particular behavior is matching, or up to what level there is variation. Of course, you have to pull all those data sets which are at same V by C ratio. Then only there is meaning in comparison of that particular aspect. Because if vehicle levels or volumes are different, then definitely it is going to have different behaviors. Okay? So why our recommendation is, based on the flow level, we should be able to compare these things. Then we put all these things into Weidmann following models. Okay, this is the cup which I was talking to you. These are the parameters which we have calibrated based on this. Of course, I'm not going to go into details what is AX, ABX. I hope that everybody knows it here. So this kind of cones, this kind of cups, we try to also develop for Indian conditions based on vehicle types. And that is what is the contribution of this particular study. Yeah, then our, based on this formula, ABX and AX value, we can get it from trajectory data, from cup for each of the vehicle category. BX add, BX multi, these values, of course, V slower also we can get from trajectory. And then B add, BX add and BX mult, these two parameters we can fix some range and then get the optimized GA value, optimized value using GA, so that we can fix some kind of solution. If you try to bring out many variations in throughout India, you can get better and better estimates, basically. This is the calibration procedure. I will not go into details of it now. So this is how motorized two-wheeler, car, bus, heavy vehicle, okay. For each of the vehicle type, we have separate ABX values for Chennai as well as for Delhi. You can find that Chennai values are little higher as compared to Delhi. The reason being, this is at different flow level and this is at different flow level. This is near capacity and this is at moderate flow levels. So what is our recommendation is, let us try to pull together at same V by C ratios, different cities, how they are performing, and can you come up with a better model or better calibrated values in terms of calibration of this particular vehicle following behaviors. This is the simulation. Yeah, of course, this length and width data we have taken from our study, previous studies. Okay, these are the free flow speed distributions. Everybody knows that, free speed distribution parameters. You can see that this is the validation. The gray one is the default 74 parameters. Of course, it is going to work well as compared to default values because they are already, okay, they are just proposed by PTV, but then we have to look for some certain our own combination, okay, our own parameters. So the 74 calibrated one is for each of the vehicle types separately AX, ABX values. That is what is the contribution, okay. And then, so this is, this particular output is without acceleration input. That means what? We have just assumed acceleration values from previous studies, okay. But still our, this result is performing better. Then this particular thing you can see that, okay, this is, the earlier one was speed, average speed, and this is the density. Both are derived parameters. Though both of these we have not given as input to the simulation model, okay. Or even if we have given input to the simulation model, flow condition is different. So based on that, we can see that this particular, the calibrated ones are performing better. Because the default values are giving little higher values, but then the orange one and blue ones, they are matching in a better way. In one or two instances, it may be little bit reverse also, but it is randomness in simulation. Yeah, still more, yeah, these are the values, default values, and these are the percentage errors. You can go through it if you want. Yeah, then what we thought that, okay, let us also try to get acceleration values from field trajectory data, and thereafter we'll see whether we can have our we can have same accuracy level or not. So we calibrated this, we got this particular acceleration values also from video data. For that also we have separately developed methodology. I don't have time here to explain that. But after that you can see that there is enormous difference. Okay, the gray one is again default values of 74, and then acceleration values are taken as just what we observed in field. Okay, then thereafter you can see that in none of the cases, this is first 5 minutes, this is second 5 minutes, and this is third 5 minutes. So we tried to validate this over different time periods also. You can see that in most of the time periods, the calibrated one and the acceleration values from field are performing better than any other default parameter. So this is how we have validated this particular model or this particular, okay, theory of calibration of 74 as well as 99. Yeah, this you can go into that. Similarly, we also work for Delhi section on same lines. You can see that this is the output of 74 model, Weidmann 74 this is. This is the blue one is the default one, and then the orange one is Orange one is the real calibrated value. This is 10 seeds, and this is of course average of that. Blue one is observed one, and then we got that. This is how it was validated over a wider range of volume. Generally, we don't get this kind of volume in field. Generally, we get some points either here or either here or either here. But in this case, we try to get all over range and then try to validate that the model is robust enough to explain the variation of volume over time. Similarly, these are the plots. Even you can see the quality of plots. These are speed density plots. We can have very good. These are the plots. These looks like they are textbook plots, but then they are actually simulated for the real field conditions. Similarly, 99 model we have developed. Again, I will not explain all parameters. Okay, there is a procedure of that also. What we try to do. We have calibrated except CC6, CC8, CC9, all other parameters are calibrated in similar fashion based on trajectory data. This is how this is the cup which was developed, and this is the CC4. This is a 50th percentile of variation what we got. This is also 50th percentile. This is 25th percentile, and so basically when the distribution is there, we have to assume some quartiles. The values which are going to represent overall situation. So in some cases it is 25th percentile, in some cases it is 50th percentile. But there is some basis that how these values have come up when we have observed so many values in field. And that is what is the message we want to pass to you, that it is not just trial and error, but there is some way, there is some logic that we have to optimize and we have to calibrate it for the real conditions. These are the calibrated Wideband 99 models. And similar exercise was done, and we found that the calibrated ones are better. They are giving better output. And you can have a look over again. This is the one. The calibrated model is giving better result. These are the plots which we have also generated. Other than speed flow, there are also speed density and flow density plots. Observations are from calibration that definitely we can calibrate 74 and 99 models well, and calibrated values with better with actual field data more and more is going to replicate better situation of simulation. Finally, we developed some application. We have created one bottleneck of 100 meters in length and one lane drop, and we try to see what is its effect based on the validated calibrated simulation model. So this is how it can say, this is the design of experiment is something like this. This is the actual 100 meter bottleneck. We can even vary it in VSIM, as you know. This is immediately on the downstream of bottleneck, and this is on the upstream of bottleneck. So we have developed speed flow plots for this, and then try to see what is the impact of this bottleneck. Similar logic also can be very well used for simulating work zones or any other incident which has happened and so on. So this is the output. You can see that the first 250 meters there is no much change. Then slightly it is dropping down. Bottleneck effect is seen. At particular point you can see that there is bottleneck. Because of bottleneck there is capacity drop suddenly because it is not being effectively used. Okay. And then thereafter you can see that during bottleneck, of course, there is a capacity drop because this is almost near to 5,000 and this is just below 5,000. Okay, so you can say that almost capacity drop is there by something like 700 to 800 PCUs per hour. And this is the one which is just on the upstream of that, and we can see that this is never reached to capacity. This is never reached to capacity. That means what? Always you will find that this particular section which is just on the downstream of your bottleneck is never going to be effectively utilized because vehicles will take so much of time and it will be never filled because this is one lane drop. So always efficiency of this particular section will be affected, and because of that infrastructure will be not used properly. This is the jamming condition which we try to create because of through bottleneck situation. You can see that this is the bottleneck created, and then this is the jamming condition which we created, and because of which we got some points in congested region also. That's it. So these are the plots which we have developed based on simulation output. This is simulated data. When there are only 100,000 vehicles per hour. When there are only 1,000 vehicles per hour, there is no bottleneck. There is no any effect of bottleneck. When you increase it to 6,000 vehicles per hour, there is some effect of bottleneck. And when you increase it further 10,000, there is still more effect of bottleneck. So the backward waves are generated, and through which we can try to specially try to get the effect of these bottlenecks. One can do a very good study based on what is the width and length of this particular bottleneck. Thank you. If any question is there, I am there to answer.